Um, so let me just check. Yeah, okay, everything's working. So my name's Mike, and I'm from the University of Nottingham. And today I'm going to be talking a little bit about how to design magnetic fields in a magnetically shielded cylinder. And as Niles just said, I mean, low field environments are required for a variety of different things, such as MET and things like that. But also for an array of high sensitivity cold atom experiments. And usually this requires multiple layers of high permeability material to achieve the required background field. Has somebody got their mic turned on at the back? Sorry, thanks. And what we'd like to do is we'd like to incorporate the interaction of high permeability materials into magnetic field design so that we can potentially reduce the number of layers of high permeability materials and hopefully reduce the cost of these types of systems. Ideally, we'd like to formulate this interaction analytically so that we can understand the response of the magnetic field from a more fundamental level. But as well as that, it also provides a fast and effective design route in order to design these optimal coils. A lot of the time with finite element methods and things, numerical methods, they obviously take quite a long time, 35 minutes to get a good coil design. But on top of that, you also have numerical aberrations as an artifact of the discretization of the finite element grids. So the system that we want to look at is we'd like to formulate this problem with a cylindrical passive shield with a cylindrical active coil system inside. And to do that, we first need to understand the required boundary conditions that need to be implemented into our model. So the interface conditions at a material surface require that the parallel component of the magnetic field B and the perpendicular components of the magnetic field strength H be continuous across the boundary. So for a closed cylinder, a closed high permeability cylinder of length Ls and radius rho s centered about the origin that's got a permeability much greater than 1, we can approximate these boundary conditions on the cylindrical surface. And what that requires is that the radial components of the magnetic field be 0 on the planar end cap at plus or minus Ls over 2. The azimuthal magnetic field be 0 across the whole domain of the magnetic field, and the axial magnetic field be 0 along the cylindrical surface of the shield. And for materials such as mu metal are typically used as magnetic shields of the order of 20,000. Only small deviations of the order of 1 over mu r are actually seen. So these are most likely not the largest source of error in a physical realization of the system. We can probably say that the approximation that we're using, the magnetic field is approximately 0 for the different components in the different locations on the cylinder, approximately 0. And this is a valid way to model the interactions. So now we understand the boundary condition, we've got to formulate the problem so that we can find an expression for the response of the magnetic field in terms of initial current source. So to do that, we generate the magnetic field, and the magnetic field is expressed by contributions of initial current source H generated by a coil that's interior to the cylinder. But there's also the magnetization M, which is the magnetic field generated as an induced response to the initial current source. And this magnetization can be cast into an equivalent pseudo current density J, and using the vector potential, that allows us to relate that to the Poisson equation, but then has Green's function solutions for an arbitrary current density J, where J is both the initial current source and the pseudo-induced current density on the cylindrical shell. So let's talk a little bit about cylindrical coil design. So, so for a cylindrical coil of length L1 minus L2, like on the diagram on the right-hand side, with radius rho c, the vector potential can be written in cylindrical coordinates, and then a cylindrically expanded Green's function can then be used in order to generate a set of governing equations for the vector potential that will allow the interaction between the cylindrical shield and the cylindrical coil to be formulated in the easiest way, with an appreciation of symmetries. Everything becomes a lot easier. So what we're going to do is we're going to use a combination of methods to match the boundary conditions. And so what we're going to do is we're going to match the boundary conditions on the radial surface using a pseudo current density that is induced on an infinitely long cylinder. And then we're going to subsequently then use the method of mirror images to find the total magnetic field generated by the system. So to match the cylindrical condition, we require that the axial magnetic field be zero along the cylindrical surface of the boundary. And it's not just along the boundary between minus ls over 2 and ls, it's over z is plus and minus infinity. And what that's going to allow us to do is going to allow us to match the azimuthal Fourier modes generated by the response of the high permeability material and by the modes generated by a cylindrical coil. And this is going to allow us to generate a Fourier relation between the initial current density J, M5, and that's the Fourier transform of the initial current density, and the pseudo current density that is induced in the cylindrical shell as a result of the magnetization. So next we can use the method of mirror images in order to subsequently satisfy the boundary condition at the planar end caps. And we can do that because the planar end caps are perpendicular to the initial current source and the pseudo current density, meaning that any subsequent reflections generated by the method of mirror images continues to satisfy the boundary condition on the cylindrical surface, thereby satisfying the boundary condition over the entire domain of the magnetic shield. So this can be understood best by looking at a graphical representation of what's actually happening to the current densities on the cylinder. So if you've got an axial current density, if you've got an azimuthal current density as seen on the left, and an axial current density as seen on the right, for subsequent reflections using the method of mirror images, the axial current is seen to change its direction of current for every odd reflection. So what that's going to mean is that we're going to end up with this infinite set of reflections where every odd current density is flip reversed in the z direction, and then every even one has the same current flow as the initial current source. And using these two methods of matching the boundary condition, that's going on to allow us to write down an expression for the total magnetic field of our system, incorporating the finite length high permeability cylinder. And what we can do is we can actually see the elements within the magnetic field that different contributions to the magnetic field. So the summation of the infinite reflections can be seen with the infinite summation of a piece. So that's every image getting moved and translated, flip reversed, and they're related to the reflected Fourier transformed azimuthal current densities, where JP is the real space current density that's obviously getting translated and flipped, translated and flipped. And this has got to be taken into account when we do a harmonic minimization, just like Niall previously just did. But as well as that, we can see the radial effect generated by the cylindrical surface, where the modified Bessel function of the second kind, K, relates to the magnetic field generated by the cylindrical coil, and the combination of the modified Bessel functions relate to the cylindrical surface of the magnetic shield. So now that we've got the magnetic field in terms of pseudo current density, we now need to propose a Fourier decomposition of this current density in order to optimize our problem to generate desired fields for specific Fourier coefficients. So we use an azimuthal current density of this form, where we've added on and changed different things, where we've taken into account for the spatially changing location of each odd and even reflection. But we've also modified the Fourier series basis, allowing for opposite axial current flow and changing location. And I won't go over this again because Niall has previously gone over it. but we use the same harmonic minimization process with the same power weighting that NAR uses in all of its biplanar coil design. And now we're in a position where we can optimize for W and Q, the unknown Fourier coefficient. And what I'm going to do is I'm going to show you a quick example of what we've done. So what we've got is we've optimized for a constant transverse field for a symmetrically placed coil about the origin that is about 95% the length and radius of the shield. And this shield is 1 meter long and it's 0.25 meters in radius. And we've optimized for 200 Fourier coefficients using 200 target field points over an optimization region that is half the radius and length of the shield. And this optimization in total took about 10 seconds to generate the coil. And what we've got is we've got the dotted lines showing current flow going anti-clockwise, and then the solid lines showing clockwise current. So these coils generate fields which are approximately 1 part in 1,000 accurate over the entire optimization region. And on the figures on the right, we've calculated the magnetic field in 3 different ways. So we've calculated the green dashed, showing the price of our law without the interaction of the high permeability material. We've also calculated it numerically using a finite element calculation in COMSOL with the magnetic shield treated as a perfect magnetic conductor. And we've in dotted blue, and we've calculated it analytically with our model shown in red. So you can see in figure C that our model is fairly accurate, and it's actually accurate within 0.002% of the numerical simulation. And not only that, but we've analyzed the model in real life situations where we've used mu metal as the permeability benchmark for the material. So we've calculated the magnetic field and the homogeneity of our coils using permeability of roughly 20,000 with a thickness of 1 millimeter, while also adding in 2 holes in the planar end cap boundaries about quarter the radius of the shield. And we only see very small errors introduced of the order of 0.05%. And these errors, with regards to the errors in manufacturing, they're there and thereabouts. So in terms of designing real-world experiments, we were fairly confident that this design methodology would work in a real-life situation, even with non-perfect systems. So we physically made an example last year with in collaboration with the University of Birmingham. So we made a 6-coil system where we generated constant transverse field, constant axial fields, transverse gradient fields, and then axial gradient fields as a compensation system for the gravity sensing experiment that they're doing in Birmingham. And these coils are accurate to sort of 1 part in 500 over the optimization region. And Peter Hobson physically made this. So he did it with a 3D printed former, and then spent many long hours winding layer after layer after layer to try and make this system. But with respect to any future systems, I think probably printed circuit boards are probably the way to go, because they're more accurate than hand wound coils, but as well as that, they're a lot easier to make, waiting in order and just waiting for a coil, as opposed to spending a month winding a coil is much more valuable time to spend. But as well as that, it costs about the same. So this coil former cost a few thousand pounds, and PCB wouldn't cost a tremendous amount more. Conclusions and future work. So what we've done is we've analytically formulated the response of a high permeability cylindrical magnetic shield to a cylindrical current source and incorporated this effect into an optimization procedure that allows the design of accurate magnetic fields in real world situations. So what we plan to do is we plan to extend the range of geometries which we can effectively optimize coil designs for. So hopefully we're going to try and do it for planar geometries, and then see if we can tailor those systems to a more MEG type system. Hopefully in the future we can have maybe an 8 or 9 or 10 orthogonal field compensation system to make a potential MEG prototype. But other than that, we're releasing the code that we've used to design all of the coils, and the code is fairly flexible in that you can ask for any desired field profile, and it will attempt to design a coil for you. And again, this is written by Peter Hobson. And we've also just recently published an archive paper on this. So if you want further details on anything that I've just talked about, then please feel free to look that up or send me an email if you'd like to. But a massive thank you to everyone who's contributed to the work, and thank you very much for listening. Does anyone have any questions?
Hi, Rasmus Settar here from Alto. So a practical question with a very nicely made cylindrical coil with a 3D printed former and so on. I guess, well, at the Mansfield Fence Center, you should kind of, you know better than I, so that's what I'm asking. So would it have been possible to also make a flex PCB with the windings, which you would then laminate onto a cylinder?
Yeah, that's a fantastic idea, and that's actually what we're doing for every subsequent design after this one.
Great.
It's due to be delivered actually tomorrow for another prototype that we're making. So yeah, you're completely right. A flexiboard PCB is definitely the way to go.
Yeah. Okay. Thanks.
And I'm not as familiar with the flexible PCBs. What size? How large can those come?
So we've been talking to a company called Trackwise, and they can actually they're based in England, and they actually make the longest PCB in the world. So they can actually make them as long as you want them, but they are limited to, I think, maybe 60 or 70 centimeters. But that's just Trackwise. So with regards to the companies, I think other companies can make larger PCBs, but I'm not 100% sure. So if anyone knows anything more, please feel free to interject.
And I had a more, I guess, specific question. It's a really lovely approach, and I was curious if you. It looks like in your modeling, you're dealing with space with a uniform shielding cylinder. That you just it's approximated as a homogeneous surface.
Yeah.
Are you able to see the in cap effects, or where these various layers of mu metal, where you actually have joined panels?
So I'm not sure. So in a physical realization of this, are you talking about?
Yeah.
Or?
Yeah.
So with respect to the actual experimental validation of it, I personally have got not really much experience in it. I'm mostly theoretical. But all of the coils that we've tested and physically made, we can see the effect of the end cap, and we can see the effect of the holes in the end cap. And they do affect it, but they're generally of the order of 2 times the diameter away in distance is when you generally see a meaningful effect. So long as the holes in your end cap are sufficiently small, they don't affect the measurement or the optimization really in any meaningful way. You can still design magnetic fields that are homogeneous to 1 part in 1,000 over your optimization region, which is sort of half the length of the magnetic shield, and have those end caps in there, and it'd be perfectly fine. If anything, the only thing it's going to really hurt is your ability to shield magnetic fields. To answer the question about the multiple layers of shielding, you don't see any of the multiple layers. One layer is sufficient to satisfy the boundary condition well enough that you don't see any change from any subsequent layers, no matter how many layers you have on your system. So yeah.
Okay, and just I realize there's when people talk about different layers of shielding, typically you're talking about a layer is actually as a composite of many laminated pieces, which is what I was referring to, not the
Oh, sorry.
complete. I apologize. That was it was an unclear, it's poorly phrased question.
So that's okay. Then I don't know if you can see the multiple layers. I have to run some more experiments to verify whether you could or couldn't see that.
Okay, thank you.
That's kind of very simple and complex question at the same time. On the flex PCB, basically how you would actually implement the coil type T, so the one that actually goes around the perimeter, because if you roll a PCB there, you will have still a huge amount of manual joinery to join those loops. For others, you can probably try to align the seam into a region without wires, but for the around the cylinder components, how would you do it in PCB?
So with all of the coils with the PCBs, what we're actually doing is every PCB is actually a biplanar system where you've got a top side of the coil and the bottom side of the coil, and then you have vias that go through the PCB in order to facilitate the joining of contours up and down the cylinder. So with respect to that, it's just every time you would like to join a contour, you move on to the other layer and then apply a joiner and then come back up through the PCB and attach back onto another contour and then continue on your path. So with respect to that, that does cost more money to manufacture PCBs, which are constantly going through different layers and popping around and popping back up. But it's definitely a more efficient way to do it than hand winding them. But if anyone's got another recommendation of how you possibly make these, I'd love to hear it.
It sounds like y'all are pretty much on the forefront, so I'm not sure anyone's gonna make your life a whole lot easier right now.
Okay. Thank you for listening. Cheers.
Thank you. Next up,